Hey guys, what's up? Eddie Aho here with KissAnalog.com. Yes, I'm back. Thanks for all the good wishes and all that. I really appreciate that, guys. Yeah, things are going good, and this is gonna be a long video, so I'm gonna just jump into it. Okay, this is gonna be a MicroCap tutorial, and I had a viewer, Scott, who sent in a couple schematics. A Class A amplifier and a Class AB. Simplified circuits, but there's some questions about how to make them work and just how to get going on them. So, and then there's another viewer, Robin, who had a question about getting better resolution on the screen. So I'm going to show both those things on this video. What I'm going to do is I'm going to kind of walk through the circuits, show a way to look at them without using math, and just a way to go through the analysis and just to play with the circuits. And with a little analysis of the circuits and understanding what's going on, you kind of start playing around and using the tool. And so that's what we're going to do. So let's jump into this video and see what you think. Alright guys, here's our circuit. It's a Class A amplifier. Now let me go up to these magnifying glasses, and this guy right here, the auto scale F6. You can hit F6 if you want, but just showing you where you can find it. And there's our auto scale. There's our circuit. We're going to do some analysis. We're going to play around with this, and first I'm going to fix it. I don't like four-way intersection. Bad habit to get into. Small circuits fine, I guess, but as you get bigger circuits, harder to tell when you print out. It's just hard to tell when you're crossing whether it's connected or not. So let's also come up here and just make that line the same. Whoops, let me grab this guy, pull it down. Okay, so just clean it up a little bit. The other thing, this number 3 is right on top of the node name 3. So just push that up, and there we go. All right. So what do we have here? We have our input signal coming through a capacitor into this network. And this is driving the base of the transistor, Q1. We have 12 volt supply over here feeding our circuit. Okay, so let's look at this in two ways. Let's look at DC analysis, okay? With current leaving the 12 volt source, it'll first come, say, hit this branch and comes down here to ground. Well, this is a voltage divider, 2 resistors, almost the same value, 30K and 20.9K. Okay, so we should about have roughly half the voltage here, you'd think, 6 volts. But let's look a little further. Now, we have a couple connections here. This guy here is, capacitor looks like an open for DC, so we don't have to worry about that. But the transistor is not an open. Current will come here and it'll bias the transistor, go through this resistor to ground. So we really have Q1 base emitter and R4 in parallel with R2. Okay, now R1 and R3 look like they're in parallel, but they're really not. Just physically on the schematic they are, but electrically they're not. Current coming through here splits up, goes this way, but has nothing to do with R3. Current going through R3 comes down, splits up, goes this way, but again, they're not in parallel, even though they might look like it. But like we say, current comes down through R3 and has 2 paths, so there's a parallel path. It can go through Q1, R4 to ground, and it can also go C2 RL to ground. So now this is AC wise, right? DC wise, this is not a path. So DC wise, we have a path here. So we have this branch basically in parallel with this branch. But really, it's this network down here, the R2 and R4 with Q1, that could be something for us to think about as we analyze this circuit. Okay, that's the DC part. Now AC wise, we do have this path. So C2 RL are in parallel with Q1 R4. So Q1, R4, they're kind of in the middle of everything. They got a parallel, AC parallel path with them, and they have a DC parallel path with R2. And then we also have our input coming in through our AC. So if there's any DC here, it'd be stripped off, but we do have an AC path. So yeah, V2 is in parallel with R2. But now, when we look at this, this is our generator, so we don't really think of it loading down our circuit. It's supplying power, right? Okay, so it's supplying a signal in here. Now, what's the purpose of these two guys? These two are setting up a voltage right here to set up our amplifier. So the voltage of our amplifier, if we have 12 volts right here, it'd be nice if this was sitting somewhere around 6 volts. Well, so if this guy is sitting somewhere around 6, and if these were the same value, that'd be great, but they're not going to quite be the same. But we do want this somewhere in the middle, and that's why these values are pretty close. Now, besides setting up a voltage level, they're also supplying current. Like I said, current comes down here, parallel path. A little bit of current goes in this. Well, that means that we have to have enough current going this way to drive this transistor that's going to drive this stuff. Well, when we look at 30K and roughly 30K, we have roughly 60K coming off 12 volts. So there's not a lot of current come down here. So this guy better have a lot of gain, because there's not a lot of current feeding that. So that's something you might want to look at, is lowering the value of those. Now, the other thing is another parallel path. This 8 ohm load, AC wise, this 8 ohm load looks like it's shorting out this, because we have a 150 ohm resistor here, and that's a lot lower. Normally, you want your source impedance, where your power is coming from, you want the impedance from that power source to be very low, like 12 volts. You want this source impedance over here very low, so there's no voltage drop between this and these components. Well, same thing here. When you're pulling this down, it's called loading your circuit down. If your source impedance is not low enough, you're loading it down. Well, what is the source impedance? If you're standing here at the capacitor looking into the source, which is this node, you have a 150 ohm path. And this path, remember, this impedance is like very low, so this path goes down to ground. So you have 150 ohms to ground, and you have a transistor. Now let's say the transistor is fully on, so there's very little impedance. So best case scenario, you have 150 ohms here. Well, that's a parallel path, right? Little current would go this way, 150 ohms, 150 ohms, 250 ohms in parallel is 75 ohms. So 75 ohms source impedance driving at 8 ohm. That's not very good. That's kind of the opposite of what you want. You really want your source impedance about 10 times less than your load. So you really want this down, say, 1 ohm or 0.8 ohms. So these guys look like they're too high a value. Okay? So now let's just do run some analysis. I'm going to come down here to the probe transient. That's kind of a nice one just to poke around. Oh, now look, it didn't fill up the space down here, the workspace. So come up to this panel where it shows 2 panels parallel. And okay, so go ahead and hit that. Okay, so see our schematic, we're kind of zoomed in too tight. So let's hit this, auto scale again. Boom. All right. Sometimes you want to zoom in on parts of your schematic. This one's small enough that we can look at it from here, I think. All right, let's just look at the input signal. Now see, I got a V tied to my cursor, so that means I'm looking at voltage. Okay, there we are. There's our signal. Yeah, we got 1 volt peak and negative 1 volt peak. So we got 2 volts peak to peak signal. And now on this side, it's going to have a DC shift because, right, we've shifted this up to some DC voltage. Is it going to be 6 volts? What do you think? Remember, these guys are in parallel, so it's going to drop the impedance of this. Nope, look at that. Now let's turn off the input signal. Just double click that. And then Now we have this. So it looks like it's centered somewhere around 3.7 volts. So it's not 6 volts like what we wanted. That's because this impedance over here is lower than this. Now, just to give you a little tip, remember the base current doesn't take a lot of current to drive this current. So from this point, if you're looking into this guy, if you're looking into the base, you're seeing a little bit of current go through there, but you have 150 ohms and you have a lot of current. So really that resistor looks like a big resistor to this base. That's because the gain of the transistor affects that. So really that resistor is the gain of the transistor times this resistor. Okay, so let's say it's gain of 100. If it's gain of 100, add a couple of zeros to that, it'd be 15K. So we got 15K and parallel 20K. So let's go ahead and drop the value of both these resistors and see how that affects that. And I'm going to make this easy. I'm going to make this a 3K because we'll just make them the same. They're so close, it's not going to really change anything. You can see our signal disappeared over there. See if it comes back. Well, kind of did. Okay, let's go auto size this window. Auto scale. There we go. Wow, look at that. Now we're right up around 6 volts. So that's looking a lot better. Now we're kind of where we want to be. All right. So I think we took care of that. Now we got enough current coming in here that this guy's not affecting this guy as much. So even though they're in parallel, the value of this is a lot bigger than this, so we're not getting affected too much anymore. So that was kind of nice to understand that, and we kind of solved that problem. Here, let's just go a little bit further on our circuit and let's look at some more stuff. Let's look at the signal. See that signal? Here, let's turn off this one. That is not a very big signal. Let's get this cursor here. Let's see what that scale is. It's right around 100 millivolts. So 100 millivolts peak to peak. Not very good. That's because remember now AC wise, this guy here is small resistors looking like it's shorting out this. So let's make this guy smaller. Let's click on this. I'm going to make it 50 ohms. That'll make it easy. Just back up space. Whoops. Got to back auto resize our window again. Whoa. Okay. Now look, two things. One is we're not up around 6 volts anymore. We're down around 3. And as this signal goes low, something happens. It just goes crazy. And yeah, I think the problem is this signal tries to go low. There's not a lot of current left to come down here. And this guy, our 8 ohm resistor, is just, I think, kind of shorting this out. Let's just look at our signal. I mean, the one improvement is we did get a bigger signal, right? I mean, 1.7 volts now, peak to peak. So that's the good side. The negative side is we're just crashing. So let's come over here and just change. Whoops. That's what happens when you click on the resistor, the RL. I want to click on the 8. I have to kind of hit this little button so I can click on this guy. All right, so let's click on the resistor here and come up here and make it 80 ohms. Well, I'm going to just change it to 100 ohms. Nice even round number. Nice round number, 100 ohms. Oh, wow, look at that. Holy cow. All right, let's change that to 200 ohms. Okay. All right. So now that we got this craziness going on, let's just come over here and see if we can drive, because it's down as we swing down low again, right? So let's come back over here and make this 300 ohms. Let's just get a little bit more drive. Well, that's still not looking too great. All right, so now I think one thing that's happening is this AC thing is this AC branch is basically shorting out this. Let's make this resistor a larger resistor, like 100 ohms. Wow, that's looking better. Okay, let's make it 200 ohms. Well, it looks like it's getting better, but you know, the thing is this is on the swing upwards. Now, when we were crashing before is because we're getting too low and we just didn't have enough drive or enough current, you know, so we're just kind of crashing over here. But now it's crashing up, you know, it's still having a problem up here. So let's go look at this transistor. I think we basically have a transistor problem. And, you know, we don't see the value on the schematic. Here, see, right here, it's 2N2222. That's a pretty small transistor. That's a signal transistor, not a power transistor. So I turned it on. So see, that's a lot better to turn on those values so you can see them. So that would have been a little bit more obvious if we had this undersized transistor. So let's click back onto this. And let me show you the trend. Okay, this guy right here, if you look down the window below, it's forward beta. We're gain of 200. That's nice. But the problem is if you come over here to these currents, see the IKF down the bottom, it says high current corner. It's like 1.77 amps. I mean, these transistors, the 2N2222 just does not have a lot of power. So what I've done before is looked up here in this window. You see the IKF larger than 4. This IKF is only 1.7. So I put this in before just to search. And let's look for transistor. Let's just try this guy right here. Okay, the gain's not near as high. It's less than half. But man, look at all the current we have. Let's try that guy. Oh, wow. Okay. Well, you know what? It looks to me like it's just a gain thing, because this is completely different, and it's when the signal's dropping low. So I think when the signal's dropping low, we just don't have enough gain to drive this guy. So we could go find another transistor, but let's just see if that's true. Let's make this a 30 ohm. Okay, let's auto scale. Wow, okay, there we go. Looking much better. All right, guys, so things are looking like, whoops, kind of forgot about our load. Our load's still 200. Let's drop that load. Now that we've dropped value, you remember this guy was in parallel with this and all that, and plus we didn't have a transistor big enough. Let's drop this back down to 80 ohms. Hardly even affected our output. Okay, let's get brave and make it 8 ohms. It's kind of crashing again. All right, we have plenty of drive, I think, and this transistor can handle the current. I think the problem is 8 ohms compared to 50 ohms over here is the problem. Let's make this guy 10 ohms. Whoops. Let's go auto scale. Well, there we go. Okay, that was a lot of work. But you know, you kind of see how you can analyze a circuit with AC and DC both, kind of simplifying your analysis, and then you know, you go back and forth and and end up with something like this. So let's just see what our signal is out here now. 1.35. So yeah, you know, we've made some improvements. Okay, we deleted all curves. Now what I want to do is I want to show you something else and make things a little nicer. Let's call this VN. And now look, if I pull this way, I want to show you something. See the little square under VN? If I hover over this line, the node name is 5. Now if I grab this and pull it down, you see how I put a red dot there? Now if I hover over this, node name is 5, comma VN. So that makes it easier when you're simulating. It gives you a name. Let's call this V out. Okay, now let's grab our probe. Oops, somehow I accidentally clicked on something. Let's delete all those curves. Okay, let's click on VN. See down here at the bottom, VN. There's our 1 volt signal, or 2 volts peak to peak if you want to call it that way. And let's see what our output is now. See, voltage wise, not getting any gain. Now current wise, this little generator, you know, whatever came through here probably wouldn't have been able to drive an 8 ohm load. So we did get some current gain, but no voltage gain. Okay, I want to show you something that maybe you've already spotted it, but it's just another thing to think about. Now, to turn on a transistor, you need to put 0.7 volts there, right? Well, remember we're biasing this up around 6 volts. Well, when you think about that, you got 6 volts here, 5.3. You got a lot of current that's going to go through this resistor. So you're putting a lot of current in this. And that means this transistor has to be on, you know, pretty hard. That might kind of make you think about these signals over here. See how they're in phase? Well, that's because, here, look, let's come over here and look at the emitter here. Okay, should be just 0.7 volts different, right? Let's look at the, here, let's turn off these two guys. And then I'll come over here and click on the base. Okay, so now you can see the base here. That's node 2, right here, the red one, okay? And the green one, our emitter, is just down a little bit lower. But now let's click on this guy up here. And look at that. You notice that? Here, let's clear all the waveforms again. So that way we can start, our colors start getting kind of messed up because it keeps track of waveform 1, 2, and when you turn them on and off, it kind of gets messed up sometimes. So, okay, let's go back here and look at the emitter. I'm trying to highlight that node right there. Okay, and let's highlight this guy. Look at that. They're the same. This transistor, it's on. It's just pretty much solidly on. And this guy's wiggling, and both this and this side is just wiggling along with it. So we don't get any gain with that, right? But they are in phase. We are getting current gain because we have plenty of current for 8 ohms. But yeah, so this circuit here, a little bit too simple maybe for a real amplifier. So now with this circuit here, you could see how maybe you'd go, okay, you could think it through. Okay, I'm going to set up the bias of this. I want a certain voltage here, but I only want a certain current going through here. So you could set things up in a way that you could start building your circuit the way you want it to. But all right, hope that helped with this circuit. Let's go on to the next. All right, so this one here, this circuit here, let's go ahead, same thing, magnifying glass is up here, oscilloscope F6, and there's our circuit. Here's a 4-way intersection, and I spot those pretty quick. Let's just move that over to the voltage source. Okay, that's our 12 volt source, same 12 volts feeding another circuit. Okay, now looking, here's our input coming in through a capacitor. Again, capacitor feed, another four-way intersection. Let's get rid of that thing. Uh-oh, look at that. Let's undo that. And that is because this window right here, rubber banding, I got to turn it back on so it'll rubber band. Let's move my capacitor up. There we go. Now, nice, clean, easy to read schematic. This guy here, a little bit close, I can't tell. You know what? That guy right there, kind of hard to tell where that's connected, right? Oh, you know what? This diode and resistor were overlapping. Okay, let's move this resistor up even higher. And let's get this up. See how the line is green? Right through here. So what I do is I try to set this right in between them. Okay, I'll grab the transistor, move it up. There we go. Alrighty. So this guy right here, I'm kind of wondering if they're overlapping. Let's move. Yeah, these things are a little bit close here, it looks like. Tell you what, I'm just gonna go ahead and grab all this stuff right here. I'm gonna pull it up a little bit. Okay, and pull this transistor up. Now I want to pull this close to that resistor so I can make sure these guys are connected correctly. Yeah, it looks like, all right. Now I can just grab this and move it out. Yeah, it looks like there's a junction there. Move this other way. Those guys are connected right on top of each other, but it looks like they're connected okay. All right, seems like we're good. Just want to make sure everything's connected before we start. It's a good thing to do is inspect your circuits before you start trying to analyze them or solve them. You might have a problem, like, see right here? There's a little bit of a line left right there that was drawn. You see that right there? Let's just delete that. That was just an extra line. You could end up with I've had that happen before where I accidentally leave a wire trace underneath the resistor component and it's shorted. And I finally find it later when I look at it close. We're zoomed in here pretty close. We can see things pretty well. But okay, let's go ahead and run the simulation. Well, first let me walk you through the circuit. Input comes in. Now we have this resistor divider here setting up a bias on this transistor. So that's pretty easy to do math. 12 volts divided by 115K. We figure out the current, multiply it by that 15K, and that'll tell us how much voltage we have here. Then subtract 0.7, and then take that voltage divided by the 100 ohms. That'll tell us how much current we got in this resistor. Okay. Now that current is coming from this 1K, so hopefully that works out. That, you know, this 12 volts, basically we subtract 2 diodes from it, and we can just say, okay, what if that's shorted? So if we have, 2 diodes subtracted from this, roughly 10 volts divided by 1K, 1.1K, then so maybe we have 10 milliamps flowing through here. Then this transistor can actually turn off and shut it off. But when it wants to turn on fully, then this math here that we calculate this current has to be able to handle the voltage drop at the current times that 1K, if that makes sense to you. So 12 volts is all we have to work with. And, so, all right. And then we have these 2 transistors here, and these diodes, one diode takes care of the voltage drop across this base emitter. The other one takes care of the voltage drop across that base emitter. So these 2 diodes set the voltage, the 1.4 volts between these 2 spots, such that these 2 transistors are just at the brink of being on. So, All right, so as we bring current through here, then we're just moving these bases up and down. So the 1.4 volts here should turn on these transistors. They should be on. Now, we might want another resistor in here, something, a pot in here to turn these transistors on a little bit more to kind of adjust their bias. So that might be something we want to do, because with this setup, we're kind of stuck. I mean, hopefully these diode drops are going to equalize or be a little bit more than these and be able to turn them on. And then when this transistor goes up and down, he's just shaking both of these bases up and down with them. Okay, and then this point here is just going up and down. So hopefully there's enough current going through here to drive this. Now, first of all, we don't know what the transistors are. Let's just go turn them on. Okay, that looks like a transistor can handle a little bit more than 200, 222 that we saw before. Turn both those on. And you know what? By the way, let's just go look at that. That's gigantic gain. 3600. Wow, is that right? Kind of wondering if these values are correct. That's a 31A. Let's go to 31. All right. So you can just click these different transistors and watch these gains change. Also, there's another thing. See this level 1? You can click on this and go level 2 and say yes, and it sets up these values a little bit differently, and you kind of see which one you like better. Now I want to show you something else when you're looking at transistors. Is you can click on these transistors and scroll through and find different transistors you might want to play with. And looking at these values and everything, it could be confusing, right? So all you have to do is hit this help, and you can move all around contents. Right now we're into see, here's the contents, index, search, but we want to go to search. Let's type in BJT for BJT transistor, and then see this right here, BJT model parameters. Okay, so when you go on this BJT model parameters, just double click on it, and then look at all this. It gives you all this information, and you can kind of get a better understanding of all these things, what they mean when you open up these windows to look at your transistors. Okay. All right, so I'm just going to hit the X, get it out of here, and leave that. But oops, I thought I turned that on. Well, how come it didn't show up? Oh, it's over here. Just grab that and drag it right here. All right, so let's just do the simulation, see what this guy's doing right now. Probe transient. Oh, let's resize that window. All right, there's our input. Whoa, okay, first of all, that's a problem. I look down here, scale goes to 10 microseconds, and this guy goes right off the screen. So my guess is that this generator is slower than the one before. The other one was 1 megahertz, if you notice that. It's pretty fast. This guy is 1K. And amplitude's 1, so it's going to be 2 volts peak to peak. Let's close this guy. Here, let's go up here and go to limits. And let's change that micro to milli, 10 milli. There we go. Now we get a signal. All right. Now, the thing is, you notice how jaggedy and ugly that looks? I'm going to zoom in so you can really get a good look at that. Yeah, see that? Okay, let's go back up to this limits again. So when you're running the simulation, I'm running at 10 milliseconds now, but Here's the output start time. I could start it at 5 milliseconds if I want. Maximum time step. There's no number there. So let's just go in here and put, I don't know, let's try, what should we do? 1 microsecond? Let's try 1 microsecond. Wow, look how much that smoothed it out. Let's do the zoom thing again. Yeah, look how much nicer that looks. You just have to get enough steps in there, you know, so that you can read it. Hey, let's go backwards to that before. Well, let me. Okay. Doesn't let me undo that. Whoops. Doesn't let me undo that. So let me go back to limits again. And I'll put a 0 back in there. What I want to do is I want to show you something. If I go to, I think it's this guy right here, data points. That's the data points it's taken. It's not very many, right? Okay, now let's go back up to limits and change that to 1 microsecond. That's our maximum time step between each thing. Now, look at all those data points we're taking. So let's go ahead and, oops, turn that back off again. Okay, Robin, I think that was a question that you had on this, and I'm sure others have had that too. Now see this, how messed up this guy looks up here sometimes? Come up here and go default main toolbar. That cleans that up. All right, so let's just go ahead and see what else we see on this circuit. Let's go out to the output, load here. So once we click on this guy, if we come down here, see we have to look at the number matched up, node 9. But see the red waveform is the 9th node out here, and we got some gain there. So yeah, we're swinging. Let's see how high we're swinging on that thing. It looks like over 5 volts. I kind of got the cursor mixed in there. It's kind of hard to see. But yeah, so, okay. You know what? I think we're going to call it quits on this one. And I think I've shown you how to look at the transistors, how to change the transistors, and how to look at their characteristics. And, you know, to Robin's question on how to get a more refined look so it's not so jagged looking. That's really important when you're doing transient analysis. You want to get enough data points. So, all right. Hey guys, hope you like that. And let's go back and chat about this a little bit. All right, guys. Hey, I want to thank my patrons. Really appreciate all your support and everything. Want to say thanks to everybody. Appreciate all your good wishes and get wells and all that kind of stuff. Appreciate all that stuff. And thank you guys a lot. It's been great having the channel. Couldn't wait to get another video going, and we're gonna get some more videos following up. And yeah, so all right, hey, let me know what you think of this video, if you like that style. I just wanted to help out some viewers, and I just thought maybe this would be something you guys would be interested in seeing in the future. So let me know. And hey guys, and if you don't mind, give the video a thumbs up if you like it, because that helps the YouTube analytics and all that kind of stuff, and, you know, appreciate it. Alright? Thanks a lot. We'll see you next time.